So now look at the same window adjustment problem, but now taking the initial keyframes of landmarks, and the graph on network block goes through one, goes through again, multiple steps, till we get the optimized version of the graph, or the window adjustment problem at the very end. So, I told you about the bottleneck with the full window adjustment. Can we build a hardware-based graph network system on FPGA? That is my research question. I say yes, and we can use it with commercial off-the-shelf parts. So, first thing I came up with was the graph network window adjustment, and then go on here and we're gonna do some high-level synthesis tools to where we get to FPGA implementation, and then the distillation of that and actually putting that in a small commercial off-the-shelf FPGA. So all the way over to the right would be that small FPGA. This one on top of the Arduino board is very small, it's an Intel Cyclone 10. And then we have it inclusive with the Raspberry Pi, which you heard about earlier. And then our input sensor would be a camera. So this is the first prototype that we came up with. So our first system looked like this. Then our graph network is our info graph here. And then this is our car. We got to move a little bit, right? So they gave us a framework of how to go ahead and go build this type of sensor. So to see where we get to move in more real-time fashion, I wanted to do a system test to where I wanted to see how it performed on Raspberry Pi. And I got to here, which was my first prototype and seeing on the first 2 gigabyte Raspberry Pi. Didn't really get a good image, and it's pretty slow. 4 gigabyte, we got more map points, but still not as efficient. 8 gigabytes was probably the best commercially available, gives me the full loop close, but it's still not the best. And you can see the differences here. Less memory for the Raspberry Pi and 8 gigabytes, a full loop close, which we need to do the bundle adjustment. But we're still using between 77 between 90% of the computation power. So then our advisor, like the Seaborn, presented, hey, why don't you start testing out on this thing called a NUC, the next unit computer. This NUC is a little bit heavier, but it has 62 gigabytes of RAM to where you can actually do some damage. So now this is the original 8 gigabyte Raspberry Pi video picture. It's the same thing on the comparable image. Also too, I see these images, they're not great, but they're making small progress. With that, we get the similar image, but with a slower startup time, which is about 6x compared to 45 seconds on the Raspberry Pi, and less memory usage. I said the NUC has about 62 gigabytes of RAM, so only using about 2%, which is great, to run this algorithm. Now, with doing that, we were able to now swap out the original method, which was there for our little Marquard, which was calculating math, just actually doing a computational math. And now we're just swapping out with our graph neural network and do inference. So on the left is our stack of how we do it. We take a map object, we extract the points, and we extract the points into the node database, the edge database, and then we make our input graph. So where then that goes into now our graph neural network optimizer, and it gives us the results. So it works the same as the SLAM algorithm, but we just change one particular part. Here's our initial results. You can't really see that number at the top, but I'm gonna tell you it's very high, and that was our Hubert loss, which was over 1 million, which was terrible. But we made some mathematical errors in our graph neural network to where we did a couple of major multiplications wrong. I can go into more detail about that, but we seen it was wrong and we made a quick change. So from doing that with the same graph, we got it down to, instead of being 1 million error, we got to about 35,000 for our Hubert loss, which is substantial in how we changed it, but still not perfect. And that was our starting Hubert loss. And our lowest Hubert loss, actually for the baseline, which is the paper that we got the inspiration from, was about 0.01. And now with our method, our lowest Hubert loss was about 0.18. So still 180 times less accurate, but we're still making progress in a great direction to actually swap out and have our graph network, which does inferencing instead of actually computing. And now visually, what does that look like? This is me probably on Tuesday. These results are really very new. So this is me on Tuesday in my classroom, so I also teach 7th grade math. And so we did like a swap around just around the room just to kind of get a quick image to do a loop close. And so this is what it looks like, the original algorithm, right? And so like right before this, like it'll go through and it'll do a loop close to where it does the graph neural network. The graph optimization, the original graph optimization is just G squared up, which is no machine learning. Now, like I said, the results don't look great, but this is the graph neural network when it does machine learning optimization. So you can see it's attempting to do those edges and put it together. It's not the best, but we can start to see, even in the more closer images, you see the map points getting pulled together. And then similar to the one in the middle, where you see the blue keyframes that are all around in a circle and loop close, we can see them starting to form over here in the last picture, where you say, okay, we're getting some type of connection. And that would make sense why we have a high Hubert loss, because it doesn't look as perfect. So now with that, right? Now we need to get into actually get some actual results for start doing like benchmarking. So that's our next steps, looking at the different metrics, right? So we already talked about time, right? Startup time versus startup time originally with the Nook and the Raspberry Pi, and then loop close time. How long does it take to actually go survey a whole loop and close that? Then accuracy. So accuracy, we have a SLAM benchmarking paper called SLAM Bench 2, which actually has a whole data set of images that you can use to benchmark the SLAM algorithm. So that's the next part, because we kind of just freestyle and just use these images to get it working. But now we can actually use real images to do benchmarking. Error, so when you're moving the camera around, number of losses that you have with losing tracking, that's a very much error that we want to try and minimize. So we want to measure that as well, along with the reconstruction error. How much error do we get when it comes to actually developing that image? Then memory, just using overall memory, we just use that from like the computer like we use on the Raspberry Pi and for the Nook. And then computer resources, we just use the task manager to see how much resources we're using, along with looking at the frames per second that we use. And then there's our assisted performance. This is probably gonna be the cool part when I put it on the car. I wanna create an obstacle course to see like how it works in like in a traffic environment. So that's the end goal of this product. And then just a full system run, like seeing how the system runs on like with the other sensors and seeing how it goes. Now, I'll stop right there because I know I'm probably out of time, but all good? Okay. Well, that's pretty much where we're at right now. And then going to the future work is where the quantum stuff comes in. So now adding in the future work, we're now talking about with more computing power, we're able to add more different sensors on it. So instead of just having the RGB depth camera, which is just images, we could do LiDAR, which is light detection and ranging. That means I send a laser out, and then the laser comes back. And the time it takes to come back, I can actually see how far you are from me. Running these systems in parallel, it look kind of like this. So just like the map points, just the lasers out, right? And then adding that onto the Nook that we have for everything else available allows us to get into talking about making more accurate 3D maps. I did jump ahead real quick, but really this would be the quantum part. So now, instead of me just having a LiDAR that just shows and detects how far you are, can I actually get a redefined 3D map that's actually more accurate? So I see a new over there. Imagine if I wanted to like see a new and actually say, I want to specifically see a new, but block out this person right here, and everything else around. Using interference and using entanglement principles of quantum mechanics, we could actually get a real greater view of the 3D map of this room while focusing directly on a new by sending like signals out, splitting up the different light, and then going and bringing it back together. And so this paper exactly does that. They have two different lasers that they actually interfere with each other. They split them and then they interfere with each other at the very end, so where you actually see a different image. So that different image is the first is the skater, and the other one is then when the quantum light is on, you see the skater. When the quantum light is off, you see the car. So taking what I said about being able to see a different image is the same methodology that you can use to actually block out things and get more precise 3D maps. And then the last part talking about quantum SLAM was we took out the math from being able to do the window adjustment, and we even did a graphical network. Now we are coming into errors with that, but we're doing the best that we can. But what if we just took all of that out and replaced all of that with a quantum SLAM algorithm? Either QAOA, VQE, or even quantum phase estimation. So those are things we were able to play around with now with having our computer power and a Nook. And then lastly, quantum key description is at the very part is all of this comes back to the traffic model, right? I'm getting data, I'm getting a signal, and I'm trying to make a decision. That decision has to be sent out very quickly. Quantum key description will be the quantum communications platform to be able to do that. So bringing it all back home to the actual goal, which is the very end, which is a quantum sensor for smart traffic management. Quantum sensors are a great playground to go ahead and play around with certain things. That's all I talked about in conclusion. But I wanted to give some acknowledgments to my team that's been helping me out, definitely my advisors, my lab mates. I see everyone in the back. Definitely shout out to Aaron. Aaron did a lot of this graphical network stuff. Definitely give him a shout out because he helped me out a lot, like a lot. And then Boeing for providing the Nooks and Intel for creating those. These are my references. Any questions?
So you talked about integrating a couple of these sensors, specifically the phase of like, I don't remember what slide it was, but I think it was the next step, the second next step slide. Yes, I think it was this one, right? So from what I understand, we can actually cancel out other things and just focus on one stuff, right?
Yes.
So, do you know exactly what that would entail that you don't have yet? And yeah, basically that's what I'm
It's actually funny because I just met up with an optics person who's working here, and he gave me like the rundown, especially with this lighter. So like, have you ever seen like a Waymo car?
Yeah.
So you see like when they have a lighter on top, you
Yeah.
see how it spins, right?
Yeah.
So like, that's the hard thing because like this diagram right here is just two light lasers pointing at each other, so they only go in one direction. So you kind of control that. But how do you control a LiDAR